Welcome to this explainer. I am so incredibly thrilled you're here today because we're going to unpack the hidden, honestly, kind of impossibly small engine that dictates literally the entire modern world. We hear it all the time. Data is the new oil. But the reality is, absolutely none of that data moves, and none of our modern miracles even turn on without the foundational hardware sitting underneath it all.
Okay, let's dive into this. We interact with these things constantly, right? We completely rely on them for our safety, our communication, our health, your smartphone, your car, your smart fridge, all the way up to national missile defense systems and life-saving hospital ventilators. And here's the crazy part. They all depend on the exact same thing. They rely entirely on a sliver of silicon that's smaller than your fingernail. Without this invisible architecture, modern life just halts.
So what actually is this magic material? Well, a semiconductor is exactly what it sounds like. It's a material, usually silicon, that sits right smack in the middle of conducting electricity and blocking it. Under certain conditions, it lets current flow right through. Under others, it stops it cold. And that dual nature, that's the whole ballgame. Because it can do both, it acts as a perfect, highly controllable switch. And that simple switching capability is the absolute foundation of all modern computing.
Which brings us to the transistor. If the semiconductor is the raw material, the transistor is the fundamental building block we make out of it. It's just a microscopic switch that's either on or it's off. That on or off state, that's your 1 or 0 in digital code. But what's truly staggering here is the scale. We aren't talking about a few dozen switches. Modern chips pack tens of billions of these microscopic transistors onto a surface literally smaller than your thumbnail.
All right, let's move into section 1, shrinking to the nanoscale, the relentless physics of getting smaller. We really need to explore how humanity actually manages to fit billions of switches onto a single tiny chip.
Now, you've likely heard of this before, Moore's Law, but it's super important to understand that Moore's Law isn't some unbreakable law of physics, like gravity. It's actually just a historical observation that the transistor count on a microchip tends to double roughly every 2 years. And this observation has effectively been the heartbeat of technological progression. It's relentlessly driven 50 years of exponential computing progress. Basically, every 2 years, engineers just figured out how to make the switches even smaller.
To really grasp just how small we've gone, I want you to literally pluck a single strand of hair from your head and just look at it for a second. Just one single strand of human hair is roughly 70,000 nanometers wide. Keep that in mind, because that's our baseline for the microscopic world. Now contrast that hair with modern process generations, which are currently marketed at a staggering 3 nanometers. Now sure, 3 nanometers is largely a marketing term these days rather than the literal physical size of every single transistor, but the scale it represents is absolutely mind-bending. We're building massive, insanely complex architectures at a level of miniaturization that's just a tiny fraction of your hair's width.
Now, what's really interesting about this slide is that this relentless shrinking is starting to hit a massive brick wall. The fundamental physical limits of the universe itself are threatening to stall this progress through something called quantum tunneling. See, as we get down to that 1 to 2 nanometer scale, the physical barriers between the switches get so impossibly thin that electrons just ignore them. They start passing right through barriers they shouldn't. They effectively teleport. And obviously, you can't have a reliable switch if the electricity just ghosts right through the off switch.
Let's ground this abstract physics back in reality, though. Why do we even care about shrinking these chips down to atomic levels? Well, because efficiency equals performance. This extreme miniaturization is exactly what allowed Apple to transition to their M-series chips, for example. By making the architecture incredibly small, these chips dramatically outperform older, much larger Intel processors. It's radically transformed the speed and battery life of the everyday laptops we all use.
Which brings us nicely to Section 2, inside billion-dollar megafactories, and how to actually print the microscopic. Let's transition from the physics of the tiny to the monumental, massive scale required to physically build them.
First up, we need to clarify the global division of labor here, because the companies whose shiny logos are on your electronics rarely manufacture the physical silicon inside them. It's a split system. On one side, you have fabless companies like Apple and NVIDIA. They do the genius-level work of designing the chips, but on the other side are the foundries, like TSMC and Samsung. They do the impossibly hard, highly specialized work of actually manufacturing those digital designs into physical silicon chips.
And just to add another really fascinating layer to this whole ecosystem, we have ARM architecture. Most smartphone chips out there today run on ARM's instruction set. But get this, ARM doesn't manufacture any chips at all. They capture immense value simply by owning and licensing out the blueprint. It's a totally different yet incredibly lucrative model of value capture in this space.
Okay, let's look at how this translates to the manufacturing process itself, which is straight up science fiction. To make these chips, silicon wafers are basically photographed with light. But not normal light. A company over in the Netherlands called ASML makes the only machines in the world capable of what's called extreme ultraviolet, or EUV, lithography. These machines cost around $150 million a pop and take years just to install. Here's how it works. Step 1. A laser fires at a falling droplet of tin 50,000 times per second. Step 2. That microscopic explosion creates a highly specific 13.5 nanometer wavelength of light. And step 3, that specific light is used to etch nanometer-scale circuit patterns right into the silicon. I mean, exploding tin 50,000 times a second to carve microscopic cities is just magnificent.
And finally, we arrive at Section 3, the global silicon choke point, the concentration of power and supply. I want you to zoom way out with me now, from that microscopic factory floor to the global map. Because this amazing technology, it's created some extreme vulnerabilities.
So the crucial point we have to talk about is this. The vast majority of the world's most advanced chip manufacturing is overwhelmingly concentrated in one single company on one single island. The Taiwan Semiconductor Manufacturing Company, TSMC, makes the cutting-edge chips for Apple, NVIDIA, AMD, and hundreds of others. Literally, one company, one island. This represents a staggering concentration of power and, frankly, a massive single point of failure for the entire global economy.
And this brilliantly illustrates exactly what happens when that super fragile system experiences a shock. Between 2020 and 2023, COVID-19 severely disrupted these incredibly complex supply chains right exactly as global demand for home electronics was surging. The real-world devastation was just cascading. Massive auto manufacturers had to idle their entire factories. Think about that. They had $50,000 cars ready to sell, perfectly built, but they couldn't ship them simply because they were missing a basic $5 chip. Add in the massive explosive demand for AI training that completely drove NVIDIA GPU shortages, and the entire global supply chain just buckled.
So, as you can imagine, the world's governments received the ultimate wake-up call. Control of semiconductor manufacturing isn't just an economic advantage anymore, it is an absolutely critical national security issue. Because of this massive vulnerability, world governments are desperately trying to reshore production. We're seeing huge policy shifts like the US CHIPS Act and the EU CHIPS Act, which have committed hundreds of billions of dollars to bring chip manufacturing back within their own borders just to secure their domestic supply chains.
Which brings us to our final thought for today. The world entirely runs on silicon. It is the invisible atomic architecture supporting every single facet of your modern life. From the very device you're using to watch this explainer right now, to the cars driving outside your window. The sheer scale of human ingenuity required to make this happen is breathtaking for sure. But so is the absolute fragility of the supply chain that sustains it all. So I'll leave you with this. How does understanding this invisible engine change how you see the devices in your hands right now? Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I will catch you next time.